So last time we looked at how sequences, our arithmetic and geometric sequences, were really similar to linear and exponential relationships functions, right? That arithmetic sequence that we looked at yesterday, we wrote in point slope form, and we talked in our last unit about how there's a reason why we write it in point slope form. It's because we get this linear relationship for that sequence. For our geometric sequence, we talked again in our last unit about why we're writing it with an exponent, and what we're starting to sort of veer into is that this geometric sequence is actually giving us an exponential relationship, which we can model with an exponential function. So we're going to continue to look at that idea today. On page 3, we've got another example that we're going to look at. So for today, our sort of big example is that we have a food company that currently has 5 convenience stores, and it's considering 2 different plans for expanding its business. So plan A is what we're going to look at first. For plan A, it says we're going to look at opening 20 new stores each year. So we've got 5 stores that we're starting with, and then we're going to open 20 new ones. That would give us a total of 25 stores. And then we'll open 20 new ones, so that would give us a total of 45 stores. And then we'll open 20 new ones, so then we would have 65 stores. And then 85, 105, 125, I'm just adding 20 each time, 145, and 165. What does this remind you of from our last unit? This is kind of like what? Yeah, this is like an arithmetic sequence. So if I wanted to treat it like a sequence, I could write an explicit formula for this sequence. I'm starting with 5 stores, and I'm going to open 20 new ones each year. So that would be 20 times n minus 1 plus 5. The other option is that instead of treating this like a sequence, I treat it like a function. So if I wanted to write a function that represents what's happening here, I could write a function called a of n instead of a sub n, a of n, like f of x. And I could actually write that function the same way. If I wanted to find a future term in the sequence, we did that in our last unit. So if I wanted to find a sub 10, I could plug 10 in for n and figure out in how many years, or how many stores, I should say, would I have in this many years. I type that in my calculator. Remember to follow order of operations. We would have 185 stores. If I were to treat it like a function instead, and say what's the value at this input, what's the output value for this input, that would look the same way. And we did this last semester. We evaluated functions at a given input to find their output. Again, I would put that in my calculator. And it would give me a certain number of stores. There's a difference between a sequence and a function. I would like you, please, to plot the points that we have for our sequence here. So treat this like XY pairs and plot those points on your graph for me. if we graph our sequence, the only values that we can see in the sort of stretch of graph we have are the ones that we have listed here in our table. Okay. So we talked about this in our last unit. There is no 6.5 step, right? I can't find a value for halfway in between these. When we talk about a sequence, you have the 6th term, you have the 7th term, there's nothing in between them. These are terms in a sequence. So for my graph, I have just this collection of points. What do we call a graph like this? It has a name. We saw them last semester. What's this called? You guys know this. There we go, scatter plot. This is a scatter plot. Now, if I switch back to my function, functions are continuous. So if I'm going to graph my function, I would get all these points that were listed in the table, but I would also get the points in between them. So my function graph here in purple is a continuous line. Because it's a linear function, I get a continuous line here. So if I wanted to determine how many stores I would have open in 4.5 years, would I want the sequence or the function? I would want the function. If I go to 4.5 years, that's a point on my line, but it's not one of my red dots. It's not one of my scatter plot points. Okay? I would need the function because I need that continuity. That's what sort of fills in those gaps in between for my sequence. Questions for me so far? Okay, so this was their plan A, open 20 new stores each year. We said similar to an arithmetic sequence or a linear function. So if we move to our next plan, on the next page, plan B, this time, we're going to look at doubling the number of stores we have each year. So I start with 5 stores, and then I would double that to 10 stores. And then I would double that to 20, and then 40, 80, 160, 320, 640, and then finally 1280 for our table here for our little glimpse. What does this remind you of? Yeah, this is like a geometric sequence. So if I want to treat it as a geometric sequence, I could write a formula for this thing. That would be, oh, they told me to use B sub n here since it's our second plan, plan B. So B sub n would be, I started with 5 stores, and I'm doubling each time, so I'm multiplying by 2 each time. So this would be 5 times 2 to the n minus 1. So there's that sort of sequence format. But I could also think of this as a function. I would like you now to find the 10th term in this sequence, b sub 10, and then also find b of 14. Find b sub 10 and b of 14. What do we get for b sub 10? $5,120. And then how about for b of 14? $81,920. Now go ahead and plot the table for me. Plot that sequence for me. Get a graph that looks like this. My sort of first few points are kind of close together, and then that distance between those points spreads out farther and farther. We couldn't fit all of our points on this graph. That's okay. We got to 320. That's all that would reasonably fit here. what is this sequence graph? What did we call this? Where it's just the points? This is a scatter plot. Now, what if I were to graph the function? What would I need to do to change this so that it's the graph of a function? So if I hop back to my last problem, my red points here were my sequence, and then my purple was my function. What did the function do that the sequence didn't? Sean, what was different about my function compared to my sequence on our last problem? No, I'm looking at the last graph. The red points were my sequence. The purple was my function. What's the difference between them? Just for this last graph, the purple versus the red. What's the difference in the purple versus the red? There is all those points that we graphed at the beginning. Our scatter plot, remember? So I had a scatter plot from the red, and then what did we get with the purple? There you go. It's its own line, right? I connected all those points. So if I have the sequence graph here and I want the function graph, what am I going to do? Connect them, yeah. Because remember, a function is continuous. It's not just those little points that we picked out from our sequence. It's all the stuff in between as well. On our last graph, we said it was a continuous line because we had a line, right? Here, we don't have a line, so I'm just going to say this is a continuous curve. And then remember, the function gives me all those pieces in between the dots from our sequence, in between those points. So if I wanted to figure out how many stores I would have in 4.5 years, is that going to be a sequence problem or a function problem? Could I find the 4.5 step for a sequence? What do we say here? Could I find the 6.5 step of this sequence? You guys. Sequence. First term, second term, third term, fourth term, fifth term. Do I get anything in between there for a sequence? Here are sequence. Sequence is to multiply by 2. So every number I get is going to do what? Double, right? Multiply by 2. Do I ever have 50 in here as a step in my sequence? No. The third step is 40. The fourth step is 80 because I double it each time, right? So can I have steps in between? No. So if I want a step or a value that's 4.5, can I get that from the sequence? No, this has to be the function. So 4.5 would be here somewhere. That would be here-ish. And that's going to be this is on that purple part. That's part of the function. The sequence is only the red points that we plotted to begin with. So as we work through this unit, we're going to start to transition away from the sequence stuff that we talked about in our last unit and into functions, which we talked about last semester. So we're going to get back into function world. So we're going to see continuous graphs. We're going to see fraction input values, right? We could have b sub 10, but not b sub 14.5. When we talk about functions, I could have inputs that are decimals or fractions. So that's where we're going to head as we get more and more into the function aspect of our exponential, okay? So we've seen from our sequences, linear and exponential patterns. Now we're going to sort of formalize that exponential stuff in function form, okay? Instead of talking about it as a way to describe a sequence, we're going to look at exponential functions when I've got all those points in between. For the rest of class today, you have 2 Khan Academy assignments looking at this sort of difference between linear and exponential functions. So we looked at some scenarios here where we had a plan that was an exponential pattern and a plan that was a linear pattern. You've got some problems that are going to ask you from context. Is this describing something linear or exponential? And then you've got another problem that's going to say, if this is my table of values here, is this describing something that's linear or exponential? If this is my function, is this describing something that's linear or exponential? So that's what I want you guys to work on for the remainder of class